Hi, folks. My name is Finbar Timbers. I am a research developer at DeepMind in the Edmonton, Alberta, Canada office, which is basically on the opposite side of the world from New Zealand. And I'm going to be talking to you folks today about a new evaluation metric for agents in two-player zero-sum games that I've been working on. So some background. So a central problem to reinforcement learning is evaluation, right? We want to understand what it means for an agent to be good or strong. We have some intuitive notions, and the problem comes when we try to write those down in some formalization. Kind of the most natural metric is head-to-head play. So you take two agents, you have them play some number of games against each other, and the one that wins the most is better or stronger, and you can assess the relative strength by the number of wins and the gameplay and that sort of thing. The problem is that doesn't always work so well. One issue is cycling, and so cycling is what happens when you have some number of agents, say agents A, B, and C, where agent A beats agent B beats agent C, and agent C beats agent A. And so then it's not clear which is the strongest or best agent out of those. And it's not clear you can assign a ranking. As a more concrete example, consider the game rock, paper, scissors. There's two strategies that we're going to consider here. The first is uniform random. And uniform random, you randomly select an action according to the uniform distribution. So you have a 1/3, 1/3, 1/3 probability over choosing rock, paper, and scissors. And then you have my favorite strategy or policy, which is always rock, which every single time it plays rock. Old faithful. Now, if you were to play these two agents against each other head to head, they'd actually tie. They'd each win a third of the time. But it's clear to us as humans that always rock is not very good. There's a trivial exploit, right? Like you can just do always paper, and you're going to win every time against that. Whereas that isn't the case with uniform random. There's no strategy that can win more than a third of the time against uniform random. So most people would intuitively say that uniform random is strong. So to formalize this, we have a metric called exploitability. And so exploitability is defined as the sum of the value that the best responder wins against an agent playing in every seat. So we have this formula here where VI is the expected utility of player I, so the game, the amount of the reward that they would win playing some number of games. And so this is a great metric. If you it has the really nice property that the exploitability goes down to 0 for a Nash equilibrium. It's great. The other thing is that the exploitability is always going to be an upper bound for how much any opponent could win against the agent. So you know that it can do no worse than the exploitability. And there's an objective meaning to it. So you can say, it gives you a ranking that it's some objective meaning. And it's great. And if you can use exploitability, you should. It's a great metric, solves all your problems. However, it's very expensive to calculate. So in terms of time, it takes O of the number of states. The order of magnitude is that of the number of states. And this is prohibitively expensive in large games. So you can calculate this in a bunch of small poker variants, as an example. But if you wanted to calculate in something like Go or chess or heads up, no limit Texas Hold'em, it would be impossible. And even in games where it is possible, like for instance heads up limit Texas Hold'em, it's very difficult to do, requiring a lot of computational resources and a lot of engineering time to actually build a distributed system that's capable of doing that. However, the definition of exploitability admits a really natural extension. So if you recall, in the definition of exploitability, we have this best response term here. And what we can do is we can use an approximate best response rather than the exact best response. And we just need to come up with some approximation that is pretty good and preserves the properties that we'd like to have. And one example, so this originated in the poker community. There's a paper by William Lisi and Michael Bowling in 2017 that they presented at a AAAI workshop where they introduced something called local best response. Local best response is a metric which does, it checks out every action at a one-ply depth, which is to say it does like a one-step look ahead. And then it uses a heuristic value function to assign a value to each of those nodes in the game tree, and then just chooses the node with the highest value. This is a general concept, but you can, in poker specifically, they use the check call value function. So you say, okay, we're at a certain point in the game. The check call value function is a value from 0 to 1. So it's the probability that the current player would win if every player checked/called for every future action until the end of the game. So basically, given the current cards that you have, that your opponent has, and the face-up cards, what's the probability that you would win? And this is a very simple approximation to a best response, but this was enough to exploit the state of the art at the time. So, which were a number of abstraction-based agents, and that was pretty surprising. So it was pretty simple. And it's a great metric. It works really well. It's really fast. But the only problem is it's not clear how to extend this metric to other games, right? Because every time you want to do local best response in a new game, you need to come up with a new heuristic. And then you need to prove the validity of it. And it's non-trivial. And you don't have any sort of theoretical guarantees about that because it's a heuristic. It's also difficult to compare LBR values across games because you can't really say how strong the heuristic is, right? You could have a heuristic that's particularly good in a certain game, or you may not, and that's not really clear. So we introduce a new method here. So the method we introduce is so first I should start by saying that approximate exploitability is a general metric. So approximate exploitability encompasses local exploitability. Local exploitability is one example, but you can use any technique that you want to approximate a best response. Something that we looked into is to use to use an RL algorithm to learn this best response. So if we take any two-player zero-sum game, we can transform it into a single-player game by simply replacing one of the players with a fixed policy, and then we turn all of the decision nodes for that player into chance nodes. We can then use any standard reinforcement learning algorithm to find an optimal policy for the resulting game. And then we can calculate the approximate exploitability just as the empirical average reward that this learned policy receives when playing in each seed. So in Go or chess, for instance, say you would train some sort of RL algorithm to optimality in playing in C0, and then you would measure the reward that it receives, and then you do the same thing in C1, and you'd get some value. And you say that value is the approximate exploitability. And you can use, the standard reinforcement learning tricks like actor learner architectures, distributed computing, all of that, and scale up well. One specific algorithm that we looked at was information state Monte Carlo tree search, or ISMCTS. So ISMCTS is a variant of Monte Carlo tree search, MCTS, which runs on imperfect information games. So it's almost identical to MCTS, except that the underlying tree that it operates on is a tree of information states, not histories. Just as an aside for terminology, when I say information state, that is given some underlying state, which we refer to as a history. A history being the complete state of the game, including all private information. So in poker, a history would be the private cards, the hand for every player, and then the public cards, and then all betting actions. The information state, on the other hand, would consist of the public information as state, plus the private information for the player who's going to act. So in poker, this would consist of the public cards, all of the betting actions that have been taken, and then the hand for the player who's about to act. It's the natural thing that you'd expect to give to an agent to play in a poker game, for instance. So we know that MCTS works well in a variety of settings. We can see the AlphaZero and MuZero papers which demonstrated this, and it's a really straightforward way to incorporate search. And so we have a slight variant on ISMCTS. So the first change we make is that for every simulation we do, MCTS consisting of, during the search phase, you do some number of simulations, and that gives you visit counts. And then to choose an action, you choose an action to play, you choose the action with the highest visit count. And so for each simulation that our agent does in ISMCTS here, we sample new private information for the opponent from the counterfactual belief distribution. So the counterfactual belief distribution is a technical term, which basically just means, given that we have access to the opponent's policy during this, we're able to compute, through a simple application of Bayes' law, the correct distribution over all the different private states that the opponent could be in. Because we've seen their actions, we can back that out. And so for each simulation, we sample from that distribution, and we get a new private information. And then we search against it. And then when we're doing our search, instead of doing the standard MCTS thing and using UCT or PUCT to select an action, we instead just sample from the opponent's policy for that information state. So we just say, okay, choose an action, and we see what they do. And we think that this worked reasonably well. So here in this experiment, we used a tabular evaluator. So we have a table for each information state with the actions that were chosen and the rewards that were returned for that agent. And each step here consisted of getting a batch of data. In Leduc Poker, I think we had batches of 1,024 games. In Kuhn, I think it was 100. And we did, I think in Kuhn here, we did 10 simulations. And in Leduc, we did, I think, 800 simulations. And you can see that it very quickly learns an optimal it learns the exact best response. So what we're comparing here on the y-axis is, in these games, Kuhn and Leduc poker are very small poker variants. We're able to calculate the exact best response and calculate exactly what the exploitability is for that, and so we're able to then compare the best response. What our agent learns as the best response, and we're able to get 100% pretty quickly. For those of you aware, Kuhn poker is a very, very small game. I think it has 8 information states in it, which is why we use such small number of simulations. But it does. The point being, in these small games, our technique is able to learn the value 100% correct. When we use a neural network as the evaluator, so for these experiments, what we did is we trained a standard reinforcement learning algorithm, namely A2C, and we calculated the exact exploitability for it. And it's not great. It's actually slightly worse than uniform random. And we then played. We then ran ABR against it, and we got these values. So it's able to get, in Liar's Dice, it's something like 90, 98%, 97% of the value. And in Leduc poker, it's I think it was like 91 or 92%. So it's able to learn exactly how to exploit these agents. And again, these are small games, so it learns. So there's not a ton of improvement over time. It's the search is kind of really dominating what's going on here. We then ran a series of experiments where we trained an A2C agent in each of a number of large games, including chess, Go, Connect 4, Breakthrough, Backgammon, and Hex. And we then played ABR against that. And in the majority of games, ABR was able to learn to win more than 70% of the time, with the exception of Go and Hex. Go, it was slightly above 50%, and Hex, it was about just under 70%. So, it was able to learn to exploit these agents quite effectively. And we have some recent, more promising results that indicate that we can do even better, which we hope to write up and release soon. So moving forward, we really want to focus on performance. We think we can get better results in large games, and we want to start playing against strong agents. So, these agents are very weak, and so it's perhaps unsurprising that we're able to learn to exploit them. And so we want to, try to run in stronger agents. These are my references. So thanks a lot, and please reach out to me if you have any questions.